that one scene from Return of the Jedi where Luke gets a prosthetic hand with the ability to react? Well, this once futuristic idea is now a prominent development in our reality. Neuroprosthesis is a relatively new scientific development that allowed for the opportunity to control prosthetics with your mind. Now, that seems like a really complex system, because it is, but it can be broken down.
Basically, engineers would design a prosthetic, but the catch is that it has to be seamlessly integrated with the body. And the prosthetic itself has to be programmed to human reactions that can be responded to by the neurons. To start the process, a person can get a sensory reintervention surgery. This can map out the body's nerves responsible for a touching and motion sensation, which can then be programmed into a modular prosthetic limb, MPL, and signals from over 100 sensors that can sense, contact, force, and temperature can be converted in the nervous system into responses of physical motion. Targeted muscle reintervention surgery allows for the muscle to be connected to the prosthetic limb, so the prosthetic can be programmed with sensors around the arm or leg, and those sensors can track muscle patterns.
Neuromodulation is a technology that has the ability to activate and regulate neurons with a targeted electricity. Nerve activity is altered by delivering electrical or pharmaceutical agents directly to a targeted area. It has a wide range of value through devices and treatments that can treat diseases, symptoms, or relieve chronic pain.
Why is neuromodulation beneficial? It is very precise. For example, a popular treatment is a targeted therapy for migraines and headaches instead of pills, which go through the bloodstream before even reaching the brain. Or, pacemakers can be placed in the brain in a targeted area rather than an estimated area within the appropriate region.
Neuromodulation isn't only precise, but it also relieves a plethora of diseases. One neurospecific application includes deep brain stimulation for Parkinson's disease, which can be activated by an implant specifically designed to treat constant signals of tremors. Other examples include pelvic nerve stimulations for various disorders and incontinence, and spinal nerve stimulation for ischemic disorders like vascular or peripheral diseases. This can reduce levels of anxiety, OCD, and addiction by exploiting and isolating the abnormalities in the brain, specifically in the nucleus accumbens, or the motivation center. How do these words relate to each other? Well, first, let's start with the obvious. They both involve neurology and the nerves that map our bodies. But how I like to see it is that you need neuromodulation in order to materialize it into a neuroprosthetic.
The hand and fingertips have very receptive and tiny nerve endings that make your hands one of the more sensitive parts, while competing with the lips and feet. Not only is the inside of the hand very complex, but the anatomy of the outside is arguably just as complex.
There are three nerves, the median, ulnar, and radial, that carry out the basic functions of a hand. The median nerve starts at the shoulder and performs precise motions and pinching actions, as well as controls the sensation of the thumb, index, middle, and one side of the ring finger adjacent to the middle finger. It is the only one that enters the hand through the bone space in the wrist, known as the carpal tunnel. The ulnar nerve, which is the body's largest unprotected nerve, runs through the arm, the hand, and connects to the pinky finger and the side of the ring finger adjacent to the pinky finger. The nerve performs a grasping action, and fun fact, when you hit your funny bone, you hit the ulnar nerve, and that's why it hurts so badly. The radial nerve runs through the arm and controls the extension of the wrist and the position of the hand. The sensory nerve sends messages from the back of the pinky finger and the side of your ring finger closer to the pinky finger, like the ulnar nerve.
Now, onto the prosthetic itself. Bionic arms work by sensing, via electrodes, when the muscles in the upper arm move, causing the artificial hand to open or close. Each electrode controls one of the motors that moves the prosthetic's arm's joints. Also, each finger will have to be uniquely programmed, reaching all the way up to the wrist, or even the arm, depending on how large the prosthetic is. The programs will have sensors all the way around each finger so that they can mimic the functions of the three nerves.
Essentially, prosthetic arms are harnessing the power of your nerves and muscles in the residual arm in order to teach the hand how to move. With training, the hand learns what the signals from contracted muscles in the residual limb are meant to accomplish and becomes trained to react accordingly.
Thanks to scientists, engineers, and inventors, there is hope for a better lifestyle for those who are disabled.
The future is now.